All right, so today we're going to switch gears and talk about aldol reactions. These are reactions still at the alpha position of aldehydes or ketones. But in this reaction, we can actually turn those into really good carbon-based nucleophiles. So let's take a look at a simple reaction. If you treat this with sodium hydroxide and water, you can actually get two equivalents of your starting material to couple together. And I'll show you the mechanism for how this works. And you form what's called a beta hydroxyaldehyde or ketone. This sort of reaction is way more common with aldehydes than ketones. Does anybody know why?
More reactive.
Yeah, aldehydes are a lot more electrophilic. So you can do these with ketones, but the equilibrium tends to favor the starting material side and not the beta hydroxyketone side. However, with aldehydes, you get a lot more of that desired product. All right, so let's take a look at the mechanism. The mechanism's pretty intuitive. What do you think the first step's going to be? So do you think the hydroxide is going to attack the carbonyl or deprotonate?
Deprotonate.
Deprotonate. Fastest reaction in chemistry, right? This is under equilibrium conditions. Hydroxide's not the world's best base, but it's good enough to get some of it to form the enolate. So I'm going to draw in these two hydrogens for the time being. Okay, and then you have some of your starting material around that's unreacted. So I'm just going to draw it in as an intermediate here, just so we've got more condensed arrow pushing. And at this point, our enolate can act as a nucleophile, attack into your aldehyde, and kick up electrons onto the oxygen. And then last but not least, you've got the water that was generated from your deprotonation step that can act as weak acid. And you form your beta hydroxyaldehyde. So in this case, you can see the base is catalytic. And depending on the base selection, this is going to be generally irreversible, right? So hydroxide, we said, is a weak base, or a relatively weak base. Therefore, this entire reaction can be considered irreversible. So let's make a couple notes. So aldol addition is favored with aldehydes. And that's simply because ketones are a lot less electrophilic. And then the reaction is reversible. There's a lot of different things that can favor formation of product, and we'll talk more about that later. But in general, you can consider this aldol addition to be a highly reversible reaction. Yep?
What's to stop another beta proton from being grabbed?
Say that again?
What's to stop another beta proton from being grabbed?
You mean an alpha proton?
Or, yeah, alpha proton.
So your question is, why aren't we deprotonating here and having it attack in again?
Yeah.
That's a good question.
Since you have the resonance stabilized with the charge that we...
Yeah, you could argue, hey, that proton is also an alpha proton. Can we do this more than once? In general, that's typically not observed. My guess is that's simply due to sterics. At that point, it's a pretty crummy nucleophile. It's just way too bulked up. Okay, so let's take a look at the reverse reaction. And this is called a retroaldol. And like I said in the other chapter, if you can do a backwards reaction. That's a good sign that you know how to do the forward one, right? Okay, so let's do this in reverse. If we've got hydroxide around, we know that we can deprotonate this alcohol, give us our alkoxide. And then in the next step, this negative charge can clamp down, and we can actually kick off this carbon as a leaving group. Normally, we don't ever show carbons acting as a leaving group, but in this case, it's allowed simply because we're forming a resonance stabilized enolate. And then, like we said before, you have this final proton transfer where you can end up with 2 equivalents of your starting material. Does that make sense? All right, so let's do a little bit of practice. Oops, sorry. I'm getting carried away. And so for this practice one, I'll make it worth 5 points. It's like, whose line is it anyway? All the points are made up. So we've got sodium hydroxide, water, and I want you guys to help me determine what the product would be. 5 points.
That's 50 points, I guess I have to do it.
And we'll do the mechanism below too. And then if you think you got the answer, give me a thumbs up too, so I kind of know where people are at.
Do we do the mechanism yet?
If the mechanism helps you, definitely do it. But I'll do the mechanism after the fact to help people that might be stuck. I'm just going to draw out some skeletons here. Actually, I'm going to see if I can change the color of this guy. All right, show of thumbs if you think you got it. Couple. All right, let's check thumbs again. Thumbs up if you got it. Thumbs sideways if you're working on it. Thumbs down if you have no idea what's going on. All right, looks like we've got a pretty even mixture. So let's go through and do the arrow pushing for the mechanism. And this will make more sense if you color code it. So the first step we know is going to be deprotonation. of an alpha proton. So over here we've got our nice enolate, which we said is a good nucleophile. And this can react with another equivalent of starting material. So I'm going to make this equivalent of starting material green just so we can kind of keep track of our skeleton backbone. All right, and then we formed a new bond, so I'll do that in black. And then over here, we've got a bond to an oxygen. The aldehyde hydrogen is right there. And we've got everything on there. Does that make sense so far with arrow pushing? Make sure you don't add or subtract carbons on accident. And then last but not least, we've got our proton transfer. Where we can draw our final product. And again, I'll keep the bond colors approximately the same. And voila, we've got our Aldol addition product. Does that make sense? All right, the reason I like doing this problem is I feel like it's a really good way of showing how to do the opposite, so do the retrosynthesis. So anytime I'm doing a retrosynthesis problem, I take a look at my aldol coupled product, and I first identify my alpha and beta position. So the alpha position is where that new covalent bond was attached, and your beta is going to be the other side of that bond, right? Okay, so whenever you're doing retrosynthesis, try to cleave that bond, and then this position that's the alcohol used to be a CO double bond. It's a really easy way of doing retrosynthesis. So immediately identify your alpha and beta position. Your beta position must have the alcohol coming off, and that alcohol must have been a CO double bond in the past. All right, so now let's practice this. All right, so for this one, what starting materials would you need? So retrosynthesis arrow has this double head. I want you to give me the starting material that you would have to have. So just like before, I'll identify my alpha position. And then some people get really confused and then they're like, well, why is that not the beta position?
It didn't take place in the reaction.
Yeah, it didn't participate in the reaction. It is a beta carbon, but the beta carbon by definition has to be the carbon where the alcohol is coming off, right? So in this case, the beta carbon that we're concerned with is this one down here, which means retrosynthetically, this was the bond that we formed, which means that this bond right here used to be a CO bond. Okay. So if we look at it, we can try to color code it even. So I'll just highlight this in blue. Say, all right, this must have been one portion of our starting material. And let me change colors here. And then I'll do the other one in purple. And then this must have been my other starting material. So if we look down here, it's going to look ugly. But do you guys see how that OH bond is now a CO double bond? And that beta position also had a hydrogen, which means this was an aldehyde. And then the blue portion must have looked something like that. Are these the same or different? They're the exact same. And then all we would need to push this forward would be something like sodium hydroxide and water. Oftentimes with aldol reactions, your two starting materials are going to be identical. That way you avoid running into a big mixture of different products. You can only get one product if you only have one starting material, right? And we'll talk more about that later. Okay, so there's one additional thing you can do with this reaction called a condensation. In general, what does condensation mean?
Condensing water.
Yeah, water is coming off, right? Okay, so in this reaction, we're going to drive off water as one of our steps. So let's take a look at our simple example that we had before, and then try to explain why. Okay, so first step, we're going to form our enolate. We know that for sure. And then in the next step, we're going to have this react with another equivalent of our starting material. I know this is getting redundant, but hang in there. And then we've got water around. That was our conjugate acid, so this can take a proton back from water. And give us our beta hydroxyaldehyde. And then you regenerate your base in this step. Marcus brought up a good point before where he said there's still alpha protons available, right? So these alpha protons are more acidic than your average CH bond. So in a condensation reaction, what you're going to do is grab one of these protons. This can clamp it down and eject off a hydroxide anion. And what you end up forming is something called an alpha beta unsaturated aldehyde. All right, now going back to first term. What temperature conditions do you think will favor formation of the product, and why?
Cold, right? Because we had two equivalents to start and we combined them. There's still hydroxide both sides.
Yep, so we're regenerating hydroxide, so it's treated as catalytic. So entropy would favor formation of the products or starting materials?
Starting material.
Entropy should favor the products, right? We're getting more moles out than we put in. So in this case, heat favors formation of the alpha beta unsaturated aldehyde.
But wasn't that water from the...
So if you think about this, the reason it's favorable is you're ejecting off a hydroxide anion in this step. So you're basically increasing the amount of disorder. So let's make a few notes with this. The condensation reaction is favored at high temp. The addition is favored at low temp. Or I guess I should say low or moderate temps. Does that make sense? The other thing to consider too is that this alpha beta unsaturated aldehyde is more stable than a normal aldehyde, and why is that? Resonance or conjugation, right? So alpha beta product is thermodynamically stable. Due to conjugation. So these are the three main points you got to kind of keep track of when you're considering an aldol reaction, is whether or not there's heat applied. The other thing too is that you do run into a minor product that can be formed. And so I'll draw this in. This would be your minor product. And why do you think it's going to be your minor product?
Less favorable.
Yeah, sterically, it's going to be running into that oxygen a little bit. So you do occasionally run into a mixture of major and minor products. Yep.
When we were deciding how many moles we started with and ended with, why don't we count the 2 moles of the starting material that we started with? Because we had 2 pieces of it, so in my mind that's like 2 moles.
Yeah, that's a good point. So you are starting with this guy, and then it has to react with another equivalent of itself.
So if I was just looking at it, I would say I started with hydroxide and 1 mole of that, and then I reacted with another mole and got water. And at the end, I only have 1 organic product, water and hydroxide. So
Yeah,
I
so-
would count the moles of it.
So you're correct. You're saying there's basically, 2 moles going in plus catalytic hydroxide, and you get 2 moles out plus catalytic hydroxide. However, what I guess I should have specified was I was looking at this last step right here. Why is this entropically favorable? Why do we go past the aldol addition all the way to the condensation reaction? And it's basically because we're increasing disorder for that particular step.
So we're not talking about all the way from A to Z. We're talking about kind of this last.
Exactly. Why are we not stopping at the addition product? Why are we going to condensation? That's a really good question.
And then we're always taught that hydroxide is a terrible leading group, and won't we?
Yeah.
Is that because we're in a really basic setting? And I don't know.
Exactly. So normally I taught you guys that hydroxides and carbon-based groups are terrible leaving groups. And then I'm basically unteaching you all of that this chapter. So in a retroaldol, we saw carbon acting as a leaving group. And then in this one, we're seeing a hydroxide act as a leaving group. It's really because it's under basic conditions. And in particular, for this last reaction, the high temperature is really going to favor shoving off that hydroxide due to entropy.
It's just because it's, catalytic, right? By definition.
Yeah.
So it never happens except for when it happens.
Yeah, people get angry all the time in chemistry because they're like, you teach me all these rules and then you teach me all the exceptions and how wrong you were earlier. And it's like, yeah, there's always exceptions to these rules. So in this case, hydroxide can be counted as a leaving group.
That's great.
Is it
No
also
other times, just this one time. Right?
Just this one time for the most part.
For now.
And
For
is-
now.
Does the high temp also favor the hydroxide kicking off as a thermodynamic product?
Yeah, because it's a thermodynamic product, heat favors it. Okay, so let's just do a summary. Because students get really confused about all this. I'm not going to go through and do the full mechanism. But the addition is the one where you form the beta hydroxy aldehyde. And then the condensation is where you form the alpha beta unsaturated aldehyde. So in this case, if you want to go to this product, do low or moderate temp. However, if you want to jump straight over here, you've got to use high temp. And then you also can convert from here to here, but this must be done under high temp too. So there's a couple different ways to consider this. However, the main thing you should always look at is the temperature. All right, so all of the examples I've given you are with the exact same starting material, but let's take a look at what happens if you don't have the exact same starting material.
Should we have the reagents in there? We're missing some hydroxide.
All right,
Go with the liquid.
fair enough.
-2.
-2 for Jeff. All right, so let's look at something called a crossed aldol. And a crossed aldol is kind of a pain, and I'll show you why. Let's say I've got this aldehyde in red and this aldehyde in blue. I want you guys to determine what product or products you could get if you treat this with sodium hydroxide and water. You can assume that they're in equal amounts in solution.
What's the temperature?
You can assume that it's low or moderate temperature, so Aldol addition. Does anybody want to help with the stats of this? How many products should we get out? 1, 2, 3, 4, 5, 6. 4? 73? What's the answer to the universe? Was it 43? 42. So in this case, consider it this way, right? We could have 2 of the red aldehydes react. That would be one product. We could have 2 of the blue aldehydes react. That would be our second product. We could have a red react with a blue, or we could have a blue react with a red.
That's what I'm saying.
So we've got 4 potential products. So let's try to piece together the 2 reds coupling. So if we have 2 red products coupling, we would end up with a beta hydroxyaldehyde that looks like this, right? So that's one option. Now let's do the 2 blues. Oop. So that would be the 2 blues coupled together. And then we'll do a red and blue. So that's one option. So in this case, the blue aldehyde was the enolate attacking into the red aldehyde. Conversely, you could have one where your blue carbon acts as an electrophile, and then your red aldehyde is going to be your enolate. Sorry. So really from this reaction, if you just threw everything together, you get 4 different products out. And this is a big problem. So we have to have strategies for avoiding formation of multiple products if we do want to do a cross to aldol condensation or addition. So let's take a look at tips and tricks for only getting 1 product. Does anybody have an idea for one of them?
Chiral catalysts.
Chiral catalyst. That's a little unnecessary. Simplest one is only use 1 starting material. That's what we've been saying. Just avoid the problem altogether. It's a decent strategy. So we'll say avoid the problem.
Don't be a concrete solution.
So don't mix them. All right. Anybody have a different one? One problem I would say is our base is pretty crummy, right? Hydroxide. What if we change the base? That might actually help, right? So a really simple solution is, let's say we want the blue aldehyde to act as our enolate. All right. All you would need to do is get a really, really strong base, put that in a beaker or in a round bottom flask, and then drip your aldehyde in. As soon as the aldehyde that's dripped in touches that sea of base, it's instantly going to turn into 100% enolate before it has a chance to attack itself. Does that make sense? So you're basically playing games with your enolate formation. You're forming your enolate so quickly it never even has a chance to attack itself. That's a really good strategy. So number 2. Whoop, oh no. Come on back. There we go. So number 2 is drip the aldehyde or ketone that you want has the enolate into LDA. Let's make a note. This forms approximately 100% enolate before it has a chance to attack itself and form an aldol product. Okay, then after you've formed 100% of your enolate,
The other one.
exactly, and then drip in your electrophile.
Are you gonna, you probably need a 1-to-1 ratio for your starting aldehyde that you want to enolate to the LDA, right?
Sorry, say that again?
So if you have more LDA than you do of the stuff you want to be the enolates, it's gonna turn some of the second aldehyde into.
Exactly. So you were saying if you've got excess LDA, you might run into a problem. So we do need to be very, very careful measuring out our LDA, which is easy to do because typically when you buy LDA, it comes as a solution pre-prepared and it will tell you the molarity on it. So all you need to do is careful stoichiometry and you're good to go. So after you've made your 100% enolate, then you drip in your second aldehyde or ketone. The main thing to pay attention to is that the order of addition matters. Oop. So if I give you a synthesis problem, you have to pay attention to what's going in as your starting material and then what's going in step 2 or step 3 and so on. So make sure you pay attention to your order of addition. The third one that's actually pretty dang easy is use reagents where only one of the aldehydes or ketones has alpha protons. That's also along the lines of step 1, just avoid the problem altogether. So, does that make sense? Yep.
Since aldehydes are so much more reactive than ketones,
Mm-hmm.
could you safely say that if you put an aldehyde and ketone in together in a basic mixture, that one of them would predominantly act as the enolate and the other one wouldn't? Could that be a way to control something?
So your question was, can you favor one forming the enolate over the other based on a mixture of aldehydes and ketones? It really depends. The pKa of alpha protons off of aldehydes and ketones is going to be comparable. So the formation of the enolate could be about the same, but then your electrophile, your aldehyde is going to be a lot more electrophilic. You might still run into a mixture, which is a pain, so this is a better way of avoiding it altogether. Actually, I should say, let me rephrase this, then transfer rather than drip. So then transfer to your second aldehyde or ketone. All right, so let's take some examples of this. Sorry, I lost all my stuff here. Come on. All right, let me reopen it. Sorry, I think my adapter's on the fritz here. Okay, so let's do some practice problems. Let's figure out a way to make this compound. And make sure your order of addition makes sense. So show of thumbs again, thumbs up if you got it, sideways if you're working on it, thumbs down if you have no idea what's going on. All right, looks pretty mixed, so let's just do a simple retrosynthetic analysis. So first we identify the alpha proton, which we know must be right here. The beta proton's the site where our alcohol is coming off, and this is the bond that we made, right? So let's break this apart. We know that that is one portion of the molecule, and this must be our enolate. Why do I know it must be our enolate? Yeah, it's the one that still retains the double bond to the oxygen, and its carbon is the thing forming the new covalent bond. So this must be our enolate, which means our other starting material must be an aldehyde. So we'll say this must be our electrophile. All right, so now let's try to piece this together into a common sense approach. I'm going to draw our first starting material with our diethyl ketone there. All right, how do we form an enolate 100%? Yeah, drip into LDA. So step one, I'll say LDA. We want to drip it into the LDA, not the LDA into it, if that makes sense. And then step two, what are we going to do now? So drop it into the aldehyde, maybe? So we formed 100% of our enolate here. Now we need to introduce our aldehyde. And then last but not least, we'll treat this with water as a workup, and we can get to our final product. So these retrosynthesis problems are sometimes a little bit tricky. You have to pay attention to what goes first, what goes second, what goes third, and so on. Yep.
You have to worry about the ketone because it's symmetric, having two enolates, or I guess having it deprotonate twice because it's such a strong base.
Yeah, so you're asking, can you have the doubly anionic enolate? That's really, really uncommon. Yeah, so just focus on deprotonating one alpha proton and then having that enolate as a nucleophile. All right, let's do another retrosynthesis problem. Let's do this one. I'm going to mix it up. So devise a synthetic route. So retrosynthetically, again, identify your alpha-beta position. We know the alpha position has got to be right here. Where's our beta going to be? Okay, where the alkene ends. That means that there must have been some sort of CO double bond coming off that beta position, right? Okay, so let's kind of work backwards and break this apart. Okay, so let's focus on the right-hand side. That's pretty straightforward. We know that this one must have been our enolate. Okay, that's pretty straightforward. Now we've got to figure out what the heck's going on with the other side. What do you think our other starting material must have been? Benzaldehyde, exactly. We know that this is the bond that we just made. We always make that alpha-beta bond. So in this case, it only has one carbon coming off of the benzene. And in this case, this could act as our electrophile. All right, so now more of an abstract question. Yep.
The one that must have been enolate should be an aldehyde.
Oh, yes, sorry. This should be a hydrogen coming off here. Thank you. All right, so now the big question. How do we set this up in lab? Does the order of addition matter? Are there any shortcuts we can take? What do you guys think?
Order matters.
Does it?
Well, you have to do the LDA to the right side.
No, it does
Or you
only
do the
one. No, it doesn't because there's no alpha carbon.
Ah, you got my trick.
There's no alpha carbon.
So people oftentimes get caught up in this mentality of, well, because it's a crossed condensation reaction, we've got to be really, really particular with our order of addition. But in this case, benzaldehyde doesn't even have alpha protons. If I'm a chemist and I have the choice of using sodium hydroxide or LDA, I'm going to pick sodium hydroxide 100 times out of 100. It's way easier to work with, right? So for this one, the big thing is there's no alpha protons. So the order of addition doesn't matter. All right, so as a chemist, I'll go into my lab and I'll say, you know what, I'm just going to mix this all up. And as one of my former students used to say, shake and bake. With sodium hydroxide, water and heat. No dealing with LDA, no special order of addition, no transferring anything, and you can get to your desired product right away. Yep.
So I'm privy to what you just said, but these co-ops are said.
Yeah.
Why is it? How do we know that that methyl group wasn't coming off of? How do we know it wasn't like instead of having benzaldehyde on the left, we have a methyl group coming off of that hydrogen?
So in this case, the first thing we always do is identify that alpha-beta bond, right? And that's where the alkene is, and that's where the new covalent bond was formed. So that methyl group had to belong to the right-hand side.
Because our double bond option is coming off on the left in the beta position.
Yeah, the CO double bond must have been originally on that beta carbon. Okay, so we'll do NaOH, water, and heat. And then my last question before I let you guys go is why am I not showing this as a reversible arrow?
Because
Because
it's conjugation.
none of those things are.
It's type is conjugated, right?
Yeah, it's conjugated. We said condensation products tend to be more thermodynamically stable. This one has even more conjugation than normal due to that benzene ring. So this one's not going to go in the reverse direction at all. All right, so that's where I'm going to leave you today. When we come back next week, we'll talk about the Claisen condensation, which is a similar reaction with esters instead of aldehydes and ketones.